Hey everyone, welcome to this explainer. I am absolutely thrilled you're here. Today, we're diving right into something you probably interact with, I don't know, dozens of times a day, but might never truly think about. We're talking about water. But we aren't just looking at it as a basic natural resource today. We're going to look at water as a fascinating, incredibly complex chemical engineering puzzle. I mean, think about it for a second. Have you ever wondered what it actually takes to take a muddy, debris-filled river and make it perfectly safe to drink? It's a serious question. Today, we're following the journey of a drop, tracing the intense, almost unbelievable engineering required to turn raw water completely pristine. So, our first big milestone here is achieving what we call potable water. Simply put, this is drinking water that is completely safe for human consumption, with basically zero risk of immediate or long-term harm. It has to be clear, odorless, visually appealing, and, most importantly, entirely stripped of dangerous pathogens. Now, you might be wondering, why is this such a massive engineering challenge in the first place? Well, the stakes are incredibly high, and our usable supply is just shockingly small. Picture this. The Earth holds a mind-blowing 1.39 billion cubic kilometers of water. But get this, an overwhelming 96.5% of that is saline water locked away in oceans and seas. That leaves only 3.5% is freshwater, and a huge chunk of that is trapped in glaciers. We're literally engineering our survival on a tiny, tiny sliver of the planet's water supply. All right, let's jump into Section 1, What's Hiding in Water, also known as the universal solvent. Because water is the universal solvent, it acts as the ultimate chemical hitchhiker's vehicle, dissolving almost everything it touches. To actually make it usable, we have to defeat 4 distinct categories of natural impurities. First up, biological impurities. These are the bacteria and viruses that cause disease. Second, we have suspended impurities, which is the visible stuff, leaves, twigs, clay. Third are colloidal impurities, which are finely divided matter like clay or organic waste that just sort of stay suspended and make the water look cloudy. And finally, dissolved impurities, which are invisible gases and inorganic salts completely incorporated right into the water itself. Now, those dissolved inorganic salts, specifically calcium and magnesium, bring us to something you've probably experienced in your own shower: soft versus hard water. Soft water forms this really nice, soft, creamy lather with soap. But hard water, it contains dissolved minerals that literally react with the soap. In fact, in chemistry, hardness is literally defined as the soap-consuming capacity of water. So instead of a nice lather, those minerals create a sticky, curd-like residue. It's an invisible chemical reaction happening right there on your skin. Moving right along to Section 2, the journey to your tap, or as I like to call it, the treatment gauntlet. So how exactly do we fix all of this? Well, municipalities force our drop of raw water through a seriously rigorous 6-step gauntlet. We start with screening, move on to aeration, then coagulation and flocculation, followed by sedimentation, filtration, and finally, disinfection. And what's genuinely fascinating when you look at this process is the exact linear progression of it all. You literally can't skip a single step. You have to remove the largest objects first with screening, then add air to expel trapped gases and oxidize the iron. After that, we rely on some really clever chemistry to remove the tiny, invisible particles that won't just settle out on their own. Let's actually peek inside the plant at that clever chemistry, specifically the flocculation step. Chemicals called coagulants are added to neutralize the electrical charge of those tiny impurities. Then, the water flows right into this basin. Notice the paddles? They gently stir the water, causing those fine particles to crash into each other and clump up into larger, heavier masses called flocks. As the water moves through the basin, the mixing speed gradually slows down, so these newly formed flocks aren't accidentally broken apart. Once they're heavy enough, they simply drop to the bottom in the next step, which is sedimentation. Now, even after sedimentation, some really stubborn solids remain. That's where filtration comes in. The water percolates down through these deep, carefully engineered beds of sand and gravel. It essentially acts like a giant physical sieve, trapping those last remaining suspended and colloidal particles. But here's the kicker. Perfectly clear water can still be deadly. Just filtering it isn't enough. We have to chemically destroy the microscopic biological threats. This is disinfection. While you or I might just boil water during an emergency or an epidemic, entire cities rely on heavy-duty chemistry. They use bleaching powder or direct chlorination. Chlorine mixes with the water to produce hypochlorous acid, which is a highly effective germicide that ensures the water reaching your tap is absolutely 100% pathogen-free. Okay, so at this point, our drop of water is potable. You can pour it in a glass and drink it. But I have a question for you. Is this perfectly safe drinking water pure enough to be used in heavy industrial machines?
That brings us to Section 3, extreme water for industry, and there's zero tolerance for hardness.
So is that potable water safe for industrial machines? The answer is a resounding absolute no. For modern industrial boilers that are operating under extreme pressure and extreme temperatures to generate power, regular drinking water is basically poison. They have a zero-tolerance policy for water hardness. Any remaining dissolved salts left behind during evaporation form this soft boiler sludge that clogs up pipes, or worse, boiler scale, a rock-hard deposit that adheres directly to the walls. This drastically wastes fuel and can actually risk catastrophic explosions. So, to prevent those kinds of disasters, industries have to use elite external treatment techniques to create ultra-pure water. One of the absolute most famous methods is reverse osmosis. You see, natural osmosis naturally wants to balance concentrations out, but reverse osmosis uses intense pressure to literally fight nature, forcing the water solvent from a high concentration of impurities to a lower one through a semi-permeable membrane. The impurities are physically blocked, leaving behind exceptionally pure water on the other side. All right, let's wrap things up with Section 4, cleaning up our mess, covering wastewater and recycling. You know, once water goes down the drain of our homes and factories, it officially becomes wastewater. But before we can even think about cleaning it, engineers have to use two crucial metrics to measure the required cleanup power. First, biological oxygen demand, or BOD. This measures the amount of oxygen required by aerobic microorganisms to biologically break down the organic matter in that wastewater. Then there's chemical oxygen demand, or COD, which measures the amount of oxygen needed to chemically oxidize both the organic and inorganic material. Together, they tell us exactly what we're up against. Armed with all that data, treatment plans execute a massive, multi-tiered cleanup effort. The sewage treatment process really happens in three distinct stages. Primary treatment screens out the big physical stuff: grit, grease, floating scum. Then, secondary treatment unleashes aerobic microorganisms in these massive tanks to literally eat and biologically break down the dissolved organic waste. Finally, tertiary treatment uses fine filtration, chemical treatments, and advanced disinfection to polish that water up until it's safe enough to re-enter rivers or even be recycled for irrigation. And you know, while we rely on all this incredible modern engineering, from rapid sand filters all the way to reverse osmosis, we really can't forget where our water comes from in the first place. Sometimes, the absolute oldest practices are still the most critical for our survival. Take rainwater harvesting, for example. It's a technique that dates all the way back to the Indus Valley civilization, and it's actually increasingly mandatory in modern cities today just to conserve our precious 3.5% freshwater supply and recharge our groundwater. Which leaves us with this final thought to ponder. Water really is the ultimate traveler. And as it continues to pick up the invisible, incredibly complex traces of our modern industrialized world, the chemistry required to clean it is only going to get more intense. So how will we engineer the future to ensure every single drop is protected? Next time you turn on the tap, I hope you remember the massive hidden gauntlet of engineering that brought that pristine water right to your class. Thanks for joining me on this explainer. Keep learning, and I'll catch you next time.